Is it physically realizable to have a radius of zero? From the geometric perspective, in classical geometry, a circle is fundamentally defined by its radius. If we consider a circle with a radius of zero, it essentially collapses into a single point. This point, completely devoid of dimensions, is what mathematicians refer to as a degenerate circle. While it exists perfectly in the mathematical realm, physically, this is an infinitely small entity, invisible and impossible to draw. Now, let's talk about the area and circumference. Mathematically, the area of a circle is calculated as a equals pi r squared, and the circumference as c equals 2 pi r. When the radius is zero, both the area and the circumference collapse to zero. This means no measurable size or perimeter, hinting at an intriguing absence of physical presence. Quantum mechanics throws another curveball into this mix. It introduces the concept of wave functions, which describe where particles might be located. In a state where the position is precisely known, meaning zero uncertainty, there arises an infinite uncertainty in momentum, leading to infinitely high energy. Such a state defies physical reality as we understand it. Diving into the hypothetical, if a zero radius were physically realizable, it would revolutionize our understanding of space and matter. Imagine a dimensionless point retaining the properties of a circle. This would challenge and perhaps extend our current models of physics. In the context of black holes, a zero radius is synonymous with the idea of a singularity, a point in space where matter is infinitely dense and space-time curvature is infinite. General relativity suggests that within black holes, matter collapses to an infinitesimally small point. However, quantum mechanics predicts limits to how dense matter can become, hinting that true singularities might not exist. Stephen Hawking introduced the concept of Hawking radiation, suggesting black holes emit radiation, which causes them to lose mass and potentially evaporate entirely. For a black hole to achieve a zero radius, it would need to shed all its mass, a scenario more theoretical than observable at this point. Lastly, the study of extremal black holes, which are at the theoretical limit of size for a given charge, might provide insights into quantum gravity. As these black holes evaporate and approach what could be a zero radius, they raise profound questions about the fundamental limits of nature. So, is a zero radius circle physically possible? While it tantalizes the imagination, current scientific understanding suggests it remains a mathematical abstraction rather than a physical reality, but who knows what future discoveries in quantum physics and cosmology might reveal. Now that we've delved into the concept of zero radius and its implications in physics and geometry, let's shift our focus to the observational and theoretical evidence surrounding singularities in black holes. Are there any observations that support or refute their existence? First, let's explore the observational evidence. While direct observation of singularities is not possible, scientists infer their properties through indirect evidence and theoretical models. One significant piece of evidence comes from the detection of powerful jets of matter and radiation emanating from the centers of some galaxies. These jets, believed to be powered by supermassive black holes, showcase extreme gravitational forces at work, consistent with the presence of a singularity. Another groundbreaking discovery involves gravitational waves. The LIGO and Virgo collaborations have detected gravitational waves from black hole mergers, providing insights into the nature of black holes. The wave patterns can potentially reveal information about the central mass distribution within black holes, offering clues that may support or challenge the singularity concept. Now let's delve into some theoretical developments. One intriguing theory suggests a connection between dark energy and black holes. Recent studies indicate that supermassive black holes at the centers of galaxies might be a likely source of dark energy. These measurements show black holes growing more than expected, aligning with predictions in Einstein's theory of gravity. This could imply that black holes combined with Einstein's gravity are the source of dark energy, potentially removing the need for singularities to form at their center. Another fascinating theoretical model proposes the existence of gravastars. Gravastars are hypothetical astronomical objects made of vacuum energy or dark energy, and they do not have singularities. This model could resolve some paradoxes associated with black holes and offer an alternative explanation to the singularity concept. But what happens to matter inside a black hole singularity? According to general relativity, as matter falls into a black hole, it collapses into a singularity where the density of matter and the curvature of space-time become infinite. However, quantum mechanics suggests that there are limits to how small and dense matter can get. For instance, the theory of loop quantum gravity proposes that space and time are quantized, meaning they are composed of discrete chunks. This quantization provides a sort of quantum resistance, preventing matter from being compressed beyond a certain point. This would mean that singularities might not actually form. Other theoretical models, such as Planck stars, suggest that instead of a singularity, there could be a smallest possible volume of space that matter can occupy. This volume is not infinitely small, but is on the order of the Planck length. Similarly, the Gravastar model hypothesizes a black hole alternative filled with dark energy instead of a singularity. If these quantum gravity effects are real, they could mean that black holes are not the final graveyard for matter. Instead, they could act as temporary holding pens, with matter eventually being released through mechanisms like Hawking radiation or even explosive events as the quantum effects become dominant. In conclusion, while the concept of singularities in black holes remains a tantalizing mystery, current observations and theoretical models continue to challenge our understanding. As our knowledge of quantum physics and cosmology advances, we may yet uncover the true nature of these enigmatic entities. Now that we've navigated the realms of singularities and black holes, let's shift our gaze to some of the other exotic objects that populate our universe. These celestial wonders offer a glimpse into the extreme environments and phenomena that challenge our understanding of physics. First on our list are neutron stars and pulsar. Neutron stars are incredibly dense remnants of massive stars that have undergone supernova explosions. Imagine a star with a mass greater than our Sun, compressed into a sphere just a few kilometers in diameter. Pulsars are a special type of neutron star that spin rapidly, emitting beams of radio waves from their magnetic poles. As these beams sweep across Earth, they create a pulsing effect, much like a cosmic lighthouse. Pulsars are natural laboratories for testing the limits of physics, including general relativity and gravitational waves. Next, we have magnetars. These are a rare type of neutron star with an exceptionally strong magnetic field, thousands of times stronger than that of a typical neutron star. Magnetars are known to emit intense bursts of X-rays and gamma rays, making them some of the most energetic objects in the universe. Moving on to quasars, these are the active galactic nuclei of distant galaxies, powered by supermassive black holes at their centers. Quasars emit enormous amounts of energy, often outshining their entire host galaxies. They are among the brightest and most distant objects we can observe, providing valuable insights into the early universe. Then there are gamma ray bursts, or GRBs. These are the brightest electromagnetic events known to occur in the universe, with some lasting just milliseconds, while others can go on for several minutes. GRBs are thought to be the result of cataclysmic events like the collapse of massive stars or the merger of neutron stars, releasing energy that can outshine entire galaxies in a brief moment. Lastly, let's touch on the concept of exotic stars. These hypothetical objects are composed of exotic matter which isn't made of the usual protons, neutrons, or electrons. Instead, they may be composed of particles like quarks or even more exotic forms of matter. These stars are balanced against gravitational collapse by degeneracy pressure or other quantum properties, offering a tantalizing glimpse into the unknown.